Okay, good morning. Sorry for my delay. I was talking with a colleague and I didn't realize it was time to come in class. Let me give you the picture of what I want to do this week. This week, I want to go ahead and hopefully finalize the presentation of the material needed for using the board that you have and the distance sensor that you shall have. Why is this? This is because starting from the next week, I want to post the assignment so that by this week you have all the information needed for becoming able to develop the assignment so that you can start working. Meanwhile, I'm going ahead with the rest of the theory material that I have to present. To give you also a perspective of the month that we have ahead, we will have a number of seminars on the same line that we did with National Instruments. My point here is to make you aware of what is awaiting you outside Politecnico. So you will have the chance of listening to experts coming from different companies that tells you about the technologies that they are using, the different type of applications where these technologies that are the one that you have seen in my class are used. In particular, I'm expecting to have here FCA, the team responsible for the design and validation of powertrain systems. This means engine control unit and gear control unit. Then I'm expecting to have MathWorks as well as DSpace. So alongside with the theory material that I'm going to present, I want to give you some direct experience from companies. Having said this, let me start addressing the material that I prepared for today and for Friday. This is not yet on Portale Didattica. I will upload it as soon as I am done with the last adjustment of these slides. Let me start from this point. More or less, all of you had the chance of installing the platform support package. Some of you are still fighting with this. I received emails. We will try to sort the problem out this week. But apart from this, I hope, minor issues, most of you were able to install the platform support package, and I hope you were able to test some of the examples that we have seen together, like, for example, the LED blinking. You have seen that this platform support package is suitable for supporting the full executable export. You may remember that we have seen this a few lectures ago. So basically, once you instantiated your IOs on the Simulink schematic, once you developed your own controller logic based on state flow or based on a sequence of charts that are interconnected, you can export the whole binary. This means that the platform support package, when you ask to deploy your model to hardware, takes care of creating the scheduling of the task resulting from your model, takes care of generating the device drivers corresponding to the different IOs that you are using. It takes care of sequencing the operations. This means that if you have an input, an output, and the controller, the platform support package takes care of managing the acquisition of the inputs from the plant, applying this to the controller so that the controller can evolve according to the step function, computing the outputs, and then also always the platform support package takes care of taking the outputs and committing this to the plant. Well, this is clearly a big advantage for you because you don't have to take care of low-level programming. So you don't have to take care of C programming, stuff like that. Somebody already implemented all the mechanisms, all the low-level mechanisms that are needed to make your life easier. Well, this is the good side of the coin, but there is a back side of the coin. The problem is that you have some limitations. For sure, you have a limited expandability because if you must use an I/O that is not supported by the platform support package, you are on your own. In the sense that you need to do some low-level programming, because you need to have this support for continuing using this development model. This is normally where the software vendor kicks in, and so they charge you engineering services to make this implementation for you. When you are in a company, you have to imagine that there are different solutions for a certain problem. Roughly speaking, you always have two choices. You can go for the make solution. This means that you do whatever is needed in-house. So you have engineers that are skilled, for example, on customization of platform support package. And it is up to them to do this modification for the company. This is an investment that the company is doing in-house. And this is also a solution that requires some long-term investment, because once you do the customization, it is up to you to maintain this customization. And then if the person that was responsible for this project quits, well, you are lost, because you have lost the knowledge of the developer of this support. The other option is the buy option. This means that when you need something, you can buy the service from a company. It could cost more upfront, because it is a cost that you have to pay for buying some hours of an engineer from another company. But you don't have to make a huge investment on the long term, because if you want to have updates on the platform support package, you don't have to stay with your engineer and pray him not to leave. You just have a company that is offering a service to you. Then there is also another big issue. If you have a problem with the platform support package that is made in your company, it is up to you to solve this. If the problem shows up in something that you buy from a supplier, it is up to the supplier to solve the problem. So this is to say that if you want to use platform support package, sooner or later you will run into this problem. You will have to support a new I/O, and you have to do some modification to the platform support package. This is happening. Let's imagine that you asked a company to develop a platform support package for your electronic control unit, and then you engage with a company that wants to buy your ECU with your application, but with a customization for a different application. Well, in this case, you need to modify your platform, you need to modify your platform support package, you need to modify maybe only marginal modification, but you may need to modify your application. And so you may run into this problem, unsupported I/O. Another problem that is more intrinsic into the structure of the platform support package is the limitation on the capability of stretching or tightening the scheduling period. Let me give you an example to catch this point. Let's imagine that you have to consider the ultrasonic sensor that I hope you got. So this device here. Well, if you look into the spec of this device, you can see that the sensor has a maximum range of 4 meters. This means that the ultrasonic pulse that is emitted by this sensor can be reflected up to a distance of 4 meters, while the minimum range is 2 centimeters. So if you have an object within the emission cone of this sensor that is 15 degrees, that is placed from 2 centimeters to 4 meters, you are able to measure the distance. Well, if you look into the specs, you will see that this device is based on the time of flight of the echo that is generated by the object that reflects the ultrasonic pulse emitted by the sensor. And this echo gives rise to a pulse. The time duration of the pulse is proportional to the distance. Well, the equation is the following. 400 centimeters, so 4 meters, corresponds to a pulse duration of about 23,000 microseconds. This is because the range in centimeter is obtained by measuring the duration of the pulse in microseconds and divided by a constant that is 58. Similarly, a range of 2 centimeters corresponds to 116 microseconds. So, if you want to handle this sensor, you must be able to measure some hundreds of microseconds as duration of the pulses. The problem is that the platform support package that we have from MathWorks allows to set a minimum step size of 1 millisecond. You can try this when you configure your platform support package with a step size shorter than 1 millisecond. You will have an error when you try to deploy on the hardware. So we have a problem here. The platform support package is okay for slow peripherals, for slow IOs. So it will be okay for part of the assignment that you have to do. For another part, it is not okay. If you want to handle this, and you will have to handle this, the platform support package is not enough because we cannot handle this kind of device that is too fast. So, which is the solution here? Well, the solution here is to do algorithm export. This means that we design the algorithm we have to implement, let's say the filtering of the input coming from the distance sensor, plus some operation on the filtered data. Using Simulink, we will generate the code resulting from that model, exporting only the algorithm. Then the algorithm will be integrated manually with a custom-made software that is responsible for handling the low-level details of the communication with the sensor. If you remember, we have seen this picture before when we analyzed the architecture of the target system, where we have hardware, when we have a custom software platform to deal with the scheduling and the low-level handling of IOs. And then we have the top-level application, that is the control application, that is typically generated through algorithm export. Well, what I want to show you here? Well, I want to show you how it is possible with a minimum amount of programming to implement the custom software platform. So we give some space also to the computer engineers that are seated here, because otherwise they think they will be jobless once graduated. So here we will see how to implement the custom software platform, how to deploy this on the board, and how to merge this with the control application. The first one is coming from MathWorks, so from the flow that we have seen so far. The second one is coming from an online compiler, so no need to install any new software on your machine, okay? So don't worry with the setup problems. Let me go to the exercise in detail so that I can explain all the different ingredients that I want to show you today. This part is relevant for the assignment as well, because one part of the assignment will be to handle this, and you can't do that only with the platform support package. I am already presenting you the whole code, so you will have a good starting point for developing your assignment. So let me define the details of what we want to do. The sensor that we have here, if you look at taking it out from the box that you have, is provided with 4 connectors. The first one is the VCC, it is 5 volt. Then we have trigger and echo, and eventually we have ground. Okay. Trigger is an input for the sensor. Trigger is the input that you have to pulse in order to have the sensor that is able to start the measurement. This pulse shall be at least 10 microseconds wide. So you pulse the trigger, and then once the trigger is pulsed, the sensor works and provides you on the echo output a pulse whose duration is proportional to the distance of the object. So when we want to address the design of whichever application that makes use of this, we have to decouple the application logic from the low-level handling of the sensor. In particular, the software platform that will provide the service to allow the execution of the application shall be able to trigger the sensor, read the distance, and then provide the distance to the step function that will make use of this distance. So with the platform support package, you are probably thinking of using the GPIO output to trigger the trigger input of the sensor, and the GPIO read for reading the echo output produced by the sensor. Well, this is not suitable because the sensor is too fast for the platform support package provided on Mattworks to be able to capture properly the signals coming from this sensor. So we need to do something different. So we need to partition our application in 2 pieces of software. One is custom written using some C code, and the purpose of this code is just to trigger the sensor and read the distance. Then the distance will be provided to the control application that will do whatever else is needed. Okay? So, first point, how to trigger the echo, how to trigger the sensor, how to get the echo. Well, I can show you a piece of code here that is coming from www.mbed.org. We will switch to this in a minute to explain how it works. For the moment, let me just go through this code, trying to explaining what we have to do and then why I did it in this way. So think about the sensor. The sensor, as we said, has 4 terminals. One has to be connected to 5 volt, another one shall be connected to ground. Then we need to use 2 IOs of the board. One is for generating the trigger output. It is an output for the board, an input for the sensor. And then we need to use another IO for getting the echo input. Is an input for the board, it is an output for the sensor, okay? So basically we need to be able to write a piece of software that says, I want to use this pin as an input, this other pin as an output, and then I want to generate the desired waveform on the output, and then I want to react on what is happening on the input. This is the rationale. So how we do that? Well, using an hardware abstraction language that is, an hardware abstraction layer that is provided by Mbed. We will come to this in a minute. We can specify that a certain object of our code is a digital output. Digital out is a data type provided by this hardware abstraction layer to define an output associated with one of the pins of the board. The digital output is called trigger, and then the string that we have here between parentheses is the physical location of the digital output on the board. Well, we will see this in a minute. If you look at your board, you will see that you have two rows of connectors. Well, these connectors contains multiple sockets. Each of these is assigned with a specific label. Well, D2 is one of these labels. So with this single instruction, we are saying that the D2 pin on the board has to be recognized as the trigger object of type digital output. So the result of this is that my board, once programmed with this code, will make the pin corresponding to D2 as an output. Okay? Is this clear? Well, this is basically the same that you do when you take on the platform support package the digital write block and you select pin D2. It's the same story. The same holds true for the other one. In this case, we need an input, echo, that is an object defined in this program, is associated with pin D4. This D4 has to be managed as an input, but not just a normal input, but as an interrupt input. This means that when the board recognizes that there is a signal change on D4, it will treat this as the trigger of the execution of a piece of code. This is because we are not just interested in knowing which is the value of the echo signal coming from the sensor connected to D4, but we are interested in measuring the duration of the pulse that is produced on that input by the sensor. So we may want to start a chronometer when the pulse goes from 0 to 1. Then we may want to stop the chronometer when the pulse goes from 1 to 0. So we must be able to recognize events happening on the specific pin D4. Then we need to have the chronometer. We need to have some device that is able to measure time. Well, the hardware abstraction layer provides the timer type. Timer is something intended for measuring time. Then, what is the idea of my code? It is very simple. We connect the echo output of the sensor to the D4 input of the board. And then we associate two actions to the rising of the echo and to the falling of the echo. So when echo changes from 0 to 1, we execute the start function. When the echo goes from 1 to 0, we execute the stop function. So it is like we have the capability of pushing a button to start a chronometer when echo goes from 0 to 1, and then stopping the chronometer when we see that echo goes from 1 to 0. Okay? Then, what do we do in our code? Simply, we periodically generate pulses on the D2 output. You see here, we set trigger to 1, we wait 10 microseconds, and then we set trigger to 0. This will create a pulse on the D2 output with a duration of 10 microseconds. That is exactly what the sensor needs to be triggered. Okay? So, with this while loop, we continuously trigger the sensor. Then, what is happening? Well, as we associated two actions to the rise and the fall of the echo input, the following actions are performed. When the sensor responds, generating a pulse on echo, in particular the rising edge of the pulse, switching from 0 to 1, start is executed. Here we start the timer. So we start measuring time. Then, when echo switches from 1 to 0, it means that the sensor responded, provided us the pulse corresponding to the distance. So in that moment in time, it is needed to stop the time measurer because the pulse has been completed, so we were able to measure how long the pulse is. So it is just a matter of measuring, of getting from the timer the duration of this pulse, and we do this with this line of code, divided this by 58, and that is the distance in centimeter. Okay? Then, some ancillary stuff that you see here, we have the capability of defining that we want to have a serial connection with the board, and we can do some basic input-output operation on this. Well, what can we do with this piece of code? Well, basically, we can handle the sensor. The problem is, how can we write this code and how can we deploy this on the board? For this, we need to use mbed.org. Take note of this address, www.mbed.org. Hopefully, the network is working, so we can go to www.mbed.org. Okay. Mbed is a community of code and cloud-based tools, web-based tools for developers of application running on ARM microcontrollers, as the one that is inside the NXP chip that you have on the board. With Mbed, you can access to a developer site that requires login, but it is absolutely free, through which you can access a compiler. This is a web-based application that offers you a programming environment. This means that you can create programs, you can write programs, you can build programs. So what you have is an interface similar to this one. So you have a workspace where you can deploy, you can build your program. You have an area that is dedicated to writing your code. And then you have an area reporting the results of the compilation, providing notification, and so on and so forth. So let me show you how you can write the program that we just discussed on this environment. So once you created an account, you can create a new program. Mbed offers you a number of different boards. So the hardware abstraction layer, that is a library that provides you an abstraction of the different resources that are available on the different boards, is offering always the same interface. So you will always have digital output, interrupt input, timer, serial port, and so on and so forth. So from the programmer point of view, the elements that you will use for the programming will be always the same. Then the implementation of the hardware abstraction layer, by definition, will be different depending on the different hardware. So let's create a new program for the Freedom Cake64F. Let's take this out of the different templates that are available here. We take the GPIO example. We call this Freedom GPIO, that's okay. After a while, we will have a new program available. If we open this, this is the simplest program that you can create. Include Mbed.h so that your program is able to access to the services provided by the hardware abstraction layer. And then you can write your code similar to this one. Then once you are happy with the code, you compile it. The compilation is done remotely. There is a server somewhere in the world that is providing you the capability of building your code. Then it automatically downloads the binary corresponding to your program. If you want to deploy this program on the board, it is very simple. You have to connect the board to the computer through the SDA USB cable. Then you may remember that when you do that and you have the Mbed bootloader, you can remember that your your board is accessible through a storage, that is the Mbed volume. The programming is very simple. You just have to take the binary downloaded from mbed.org, and then you have to drag and drop it on the folder. When this is done, the program is completed, and you can see here that we have the behavior that we specified here. We have the red LED that is blinking with a period of 200 milliseconds. Okay? So if you want to change the color, well, I don't want to have the LED red, I want to have the LED green. Just to make the modification, build it again. Then a new binary will be provided. So it's just a matter of, again, dragging and dropping this to the volume. It takes some time, and when the board restarts, now we have the green LED. Very simple and very powerful. So let's now try to bring into this environment our application. So you can just copy paste the code. This is our code for handling the sensor. So where can we find D2, D4? Well, we can access to the Freedom Cake 64 documents. Hopefully, the network will respond, providing us a description of the different resources that are available on the board. Seems that all of you already are trying Mbed, and so the network slow it down. But by the way, just by clicking on the name of the board, you will have access to the documentation. So you have a description of all the resources that are available here. Then, if you look down, you will find that the different resources are coded with names that are available to Mbed. In particular, if you look the board with the Ethernet connector on the top, you will see that the connector that you have on the bottom right sets available different objects that are called from D0 to D7. So in our application, what we did was to connect the trigger to D2, echo to D4. So D2 is the third pin from the bottom. So we have a trigger that is connected to D2. So in my case, it is the purple. So D2. Then we have D4 for the echo. Then we need to have the 5 volt, that is the fourth from the bottom on the other connector, and this is the blue. And the other one is the ground. So, now I connected on the board, according to the code that I wrote here, the sensor. I just have to build again my code. Okay, it has been downloaded. Perfect. So now the new binary contains the code for handling the sensor. I can deploy this on the board. Okay, now the board is programmed to measure the distance. How can we see the output coming from the serial port? Well, the serial port is mapped on the USB cable that is also used for powering the board. So you need to have a terminal emulation program for this purpose. On Mac or on Linux, you can use Minicom. On Windows, you can use Teraterm or even Minicom. Let me just give you I don't remember where I installed the program, sorry. Okay, so you can see here that the sensor is measuring. I am pointing it towards the ceiling, so it is close to 2 meters. If I put my hand here, we should see, okay, now my hand is much more closer to the sensor, so you can see that it's reading about 13 centimeters. Then as I'm moving towards the sensor, the measure is updated. Then again, after 1 second, if I remove my hand, I am able to see again the measure that goes up, okay? So this is to prove that we are able to handle the sensor. What is happening in this code? The code is working in such way. We have an endless loop that continuously trigger the sensor. You can see here, trigger is 1, wait 10 microseconds, triggers go to 0. So we generate pulses on the trigger output for the board, that is the trigger input for the sensor. Then, after we did this operation, we print out distance. Where is this distance coming from? Well, distance is a global variable that we declared here that contains the measure of the object in front of the sensor. How this measure is done? Every time the echo output of the sensor produces an edge from 0 to 1, the start function is executed. As a result, we start measuring time. When the echo goes from 1 to 0, we execute the stop function. So we stop measuring time. After that, we read the value of the timer in microseconds. We divide this by 58, and that is the distance. Then we reset the timer, so that next time we restart counting from 0. How we can make start and stop be executed in response to events on the echo? Well, through this code. With this code here, we attach the start function to the rise event on the echo input. With this code, we attach the stop function to the fall event on the echo input. Okay? Then, after we printed out the distance, we wait 1 second. This is because the sensor cannot be triggered continuously. We need to have a short pause in between 2 consecutive triggers. Otherwise, there is the risk for the sensor to self-triggering. And the result is this one. So, what's the benefit of using this approach? Well, we can handle much faster resources that cannot be handled using full executable export. This is because by adopting C programming, we can access to the low-level details of the board, like, for example, the interrupt, like, for example, the capability of generating very narrow pulses, 10 microseconds, like, for example, the capability of using an hardware timer. These are resources that are not allowed within the platform support package because there is no support for those resources in the platform support package. Okay, so more flexibility. On the other hand, more complexity, because you can see here we need to do some C programming. Okay. Then the next step is to bring together the code coming from Simulink and the code you manually wrote. Before doing that, I would suggest you to test this code. So my suggestion is go on the www.mbed.org website, create an account for you, access the online compiler, try to write my code on your online compiler, and try to test it on the board so that we can be sure that the flow goes correctly. Okay? So let's do this now. I'm here. I can try to sort out any problem that may happen in this attempt.